Well, welcome back to our Vodcast, which we haven't done in a while. This chapter is going to be about solutions. And I want you to take a moment to look at these pictures and decide for yourself what evidence is there that the ocean water is actually a solution of a solid in a liquid. And what evidence, as shown by the plants and animals, proves that ocean water is actually a solution of gas in a liquid. Well, there's a couple of things now, obviously. Salt water is salty, and we can't see the salt dissolved in it, but we know that's what's there if we want to taste that. Also, you can see that the animals are alive, the fish, because they're being able to breathe the dissolved oxygen through their gills. Don't be confused, though, that thinking that this is a plant. That's a coral, an animal, looks like a plant. And again, all animals need oxygen to respire. So we're looking at a solution of salty water that covers like 3/4 of our planet, makes up 3/4 of what you are, mostly bags of salty water. So I'm going to take a moment to stop and we'll do a little rerun on the unique properties of water, and particularly about how those intermolecular forces of water make them have these unique properties.
Water is surprising stuff. The most common of compounds, water can be found in nature as a solid, a liquid, or a gas. Sometimes all three states exist at the same time. One of the surprises of water is that it expands when it freezes, making it less dense than liquid water. Consequently, glass containers of freezing water will burst, and ice will float rather than sink. Although water has an unusually high boiling point for such a light molecule, 100 degrees Celsius, water can be seen boiling up to the surface in some hot spots on Earth. The fact that water remains in a liquid state between 0 and 100 degrees Celsius makes life possible in a wide range of environments. Water is probably best known for its dissolving properties. The attraction of water molecules for itself and other molecules makes water very efficient at dissolving many ionic and covalent substances.
And that's the part where we want to make the connection between our previous chapter, when we discussed intermolecular forces, and also the chapter that we're doing now, solutions. So let's do some definitions then. You should have your PowerPoint notes out and be ready to take these notes down. A solution is a homogeneous mixture made up of individual molecules, atoms, or ions. Remember, homogeneous means uniform throughout. The substance being dissolved is called the solute. The substance that's doing the dissolving is called the solvent. We can say that a substance is soluble if it does dissolve in a particular solvent. And it's important to remember, water doesn't always have to be the solvent. For example, if you're trying to get iodine to dissolve, it's best if you use something like alcohols. Insoluble, of course, means that a substance does not dissolve in a particular solvent. So, for example, oils and fats, which are nonpolar, do not dissolve in the polar water solvent. Now, we reserve another term for those substances that are liquids and can or cannot be soluble in each other. And those two terms are immiscible and miscible. Two liquids that are not soluble in each other, oil and water, are called immiscible. Two liquids that are soluble in each other, alcohols and water, because they can both do hydrogen bonding, are called miscible. So I'm going to pause here for a second and give you a chance to make sure you have the definitions down of the basic terms that we need to start this chapter of solutions with. Now, there's many types of solutions, but water is frequently one of the what we call an aqueous solution, where water does the dissolving. And water is often referred to as the universal solvent. Again, that's because of its bent shape, its unshared pairs of electrons that made it bent. It has polarity, and in certain circumstances can perform hydrogen bonding. However, if you've ever had like iodine solution put on you, or perhaps maybe you've been prepped for surgery or some minor outpatient surgical treatment, you've had a tincture of iodine put on you, and that's kind of a brown color. The iodine is what gives it the brown color, but iodine is only pretty soluble in alcohol and not terribly soluble in water. So that's what we call a tincture, where the solvent is alcohol. It doesn't always have to be a solute in a solvent. For example, it doesn't always have to be a solid solute in a solvent. It could be a mixture of two or more solids. And so if you're looking at these bike parts that you see here, engineers have always been working on ways to make our metals not only stronger but also lighter. And so what you can do is melt two or more elements that are metals together, stir them together into a uniform homogeneous solution, and let them cool. And when they solidify, you now have a solid dissolved in another solid, an alloy. A special kind of alloy, I bet many of you have in your teeth right now, it's called an amalgam. And dentists still use mercury to fill in the gaps caused by dental cavities. And an alloy that involves mercury metal is referred to as an amalgam. Now here is a chart that you will find in your textbook, but I'd like to go through and point out that there are many, many types of solutions. You can have a gas and a gas. You can have solutions involving liquids with many possibilities, and you can also have solutions involving solids. Let's take a look at those. Air is the solution of nitrogen and oxygen. Sometimes it's hard to tell what's the solvent and the solute in a gas mixture, but typically we say the solvent is the one that's present in larger amounts. Well, of course, air is about 79 or 80% nitrogen, so that's why we have the nitrogen in the solvent category and the oxygen in the solute. When you look at air, it looks uniform throughout. The oxygen and the nitrogen don't separate out into layers. You can have a gas dissolved in a liquid. Anytime you've drunk a soda or carbonated beverage, you're drinking CO2 gas that's been unwillingly, by the way, dissolved into water as the solvent. We put antifreeze in radiators to prevent the liquid that cools our car engines from freezing in the wintertime. In that particular case, it's mostly water, but there's a little bit of this stuff, ethylene glycol, that will keep the freezing point at a lower temperature, and we'll explain that later on in the chapter. A liquid dissolved in a liquid, acetic acid diluted out into water makes vinegar. So vinegar is only like 3 to 5% acetic acid. Of course, you know salt and water gives you salty water. But when you look at the amalgam of mercury, a small bit of mercury as a liquid that gets dissolved into silver as a solid, that's an example when they both cool and harden of a solid dissolved in a solid. So it starts out being liquid, becomes a solid. And finally, you can add carbon to iron to make steel. And as we saw in the video on the making of samurai swords, it's to harden them as well as to allow for getting a sharp edge on the end of the blade. Now, what happens in an aqueous solution? Well, what I'd like to do is stop now. We're going to take a look at a demonstration about electrolytes. And the definition of an electrolyte is any substance that, when it's dissolved in a solution, will conduct a current. And that can only happen if there are movement of charged particles or ions. So what you're going to see, and I'll stop here, are about 6 or so demos that I'm going to do. And I'm just going to ask you as you watch this demonstration if you think that dissociation took place and if an electrolyte formed. So on that note, we'll stop this short podcast and we'll do our demo.